Hello everyone, my name is Taras Rumezhak, and I will present our team's work towards realistic symmetry-based completion of previously unseen point clouds by Ukrainian Catholic University and SoftServe. The ability to recognize the 3D geometry of the object is a key prerequisite for many computer vision applications. And this task can be accomplished by 3D scanners such as LiDARs and time-of-flight sensors. Point cloud format is commonly used for 3D shape representation, but due to the limited sensor resolution and occlusions, an incomplete point cloud can be generated as an input, causing information loss about the point cloud shape, as you can see on the damaged visualization. Point cloud completion is specifically designed to fill in the missing regions and obtain its high-quality 3D representation, as you can see on the completed visualization. So the current trend is to use deep neural networks for point cloud completion tasks. Such methods performs well on the academic datasets, but their performance drops significantly in the real-world setting, as you can see on this visualization, and degrades even further on the classes which they weren't trained on. In opposite, our framework does not require training data, can complete previously unseen objects, and is only limited by the mirror symmetry property. And here you can see the visual results of our method. On this slide, you can see the general infrastructural pipeline of our framework, and let's go through it step by step. So the first step is symmetry plane approximation. For this step, we have two ways. The first way is to calculate point normals and project them onto the unit sphere. And the second step is to compute the convex hull points and project its lights also on the unit sphere. Then, based on two spheres, we just calculate the principal components. And in this way, we will get 6 candidates to be the normal to the symmetry plane. And with the proposed metric, so-called balanced distance, we can find the best candidate, and it will be the normal to the symmetry plane. The second step is point cloud registration. So for this step, we already have the symmetry plane. We just estimate normals of the point cloud, compute fast point feature histograms, and perform global registration. On this visualization, you can see the original red plane and the mirrored blue plane, and the global registration result, which is the alignment of original and mirrored object. Then the alignment is not perfect, so we should refine it with the algorithm called iterative closest point. Here you can see a very perfect alignment. And the final step is the missing part completion. In this step, based on our metric, we just find the missing regions, as you can see here in green. And based on these found regions, we can fill in them with points and get the final result. So for the performance evaluation, we used two most common data sets, the completion 3D benchmark data set, which is based on the ShapeNet data set, and the ShapeNet data set itself with proper augmentations. We also propose our new data set of real-world scans obtained by the iPhones through depth camera. And you can see the performance of our framework on this real-world scans on this image. Here you can see the augmentation of the ShapeNet dataset with different damaged rates. So the original object and very damaged objects. Here is very interesting slide on which you can see the visual results. And as you can see, our results are better than the compared SOTA approaches as well as visually and numerically. Numeric comparison was done with the chamfer distance, which was the commonly used metric to compare the similarity between 2 point clouds. And we are better than the SOTA approaches with a moderate damage rate up to 25% and have a comparable results with 35 and 45%. And we also compared our approach with the classic SOTA algorithm to detect the symmetry plane called symmetry via registration. And we have moderate accuracy and comparable accuracy result with the original not damaged point cloud. And but we are more robust to the damages and performs better on the damaged point clouds. For the details, just see to our paper. So here are our results. And conclusions, if you have any questions, I strongly recommend you to read our paper. And if you have any questions, just drop the email to me or one of my colleagues. Thank you.